My name is Richard London. I'm a physicist. I work at Lawrence Livermore National Lab. And so the title of my talk is Evaluation of the Hazard of Dust Impacts on Interstellar Vehicles. And my collaborator is James Early, formerly of Lawrence Livermore National Lab, and now he lives a good life on the beach in North Carolina. Okay, so here's a brief outline of my talk. I'll give a very brief history, problem, definition, some properties of the interstellar medium that are important for something that wants to go through the interstellar medium. Then I'll briefly summarize the situation with the gas phase of the interstellar medium, atoms hitting spacecraft. And then I'll move on to the heart of the talk, which is dust grain spacecraft collisions. I'll talk about the energetics, and then I'll talk about numerical simulations of these collisions, including techniques, one-dimensional results, and I have one very preliminary two-dimensional calculation to show. Then I'll go on to concepts to reduce damage and conclusions and further work. So this is a partial, very personal history of my involvement, really, in the interstellar space mission concept. But shortly after the invention of the laser, Robert Forward proposed using laser-driven light sails. Jim Early came into my office around 2000 and asked me if I might help him calculate the effect of interstellar dust grains on laser sails. And I thought this was a pretty outrageous idea, science fiction, very far out. But I worked with him. It was a very interesting physics problem. And then we published this, and I thought I'd never hear about it again, of course. But then I was looking at my news feed on my computer a little over a year and a half ago, and I saw this announcement of the Breakthrough Starshot Initiative. So I got interested in this again. And this was, Phil Lubin's roadmap paper, sort of described this. A paper was written by this group here, Huang et al. With Loeb, on a very nice analysis, an analytical analysis of the problems with both gas and dust. And then I decided to try to work on this. I got a little bit of internal money from our internal research program at Lawrence Livermore to try to do these numerical simulations. And that's where I'm at. That's what I've been doing. So the problem is that the high velocity is required, as we've heard about a lot this morning. Typical velocity is 0.2 of the speed of light. So the spacecraft will collide with all the gas and dust that lies between us and Alpha Centauri or some other star you might want to go to. And each atom in either the gas or the dust carries a large energy, approximately 20 MeV per nucleon at this speed, and those collisions can cause serious damage. So it needs to be analyzed. So what are the properties of the gas and dust in the local interstellar medium that we have to deal with? There's two types of observations: astronomical, that is with telescopes observing other stars. And from these, one has concluded there's a local density in the interstellar medium of hydrogen atoms of about 0.25 per cubic centimeter. Direct observations to Alpha Centauri shows a column density along that line of sight of 4 × 10⁻17 per square centimeter of atoms. And then there's also dust. And I'll talk a bit more about this. The dust composition is mainly of two types: silicates, which have oxygen, magnesium, silicon, and iron. And most of the mass, 2/3 of the mass, are in those type of dust particles. There's also carbonaceous, mainly carbon-containing dust particles. I'll concentrate on the silicates. Then, in addition to astronomical observations, there are spacecraft measurements which detect in situ dust that penetrates inside the heliosphere. And from these measurements, a recent summary of data from the Ulysses craft by Kruger et al. Measured a density of dust of this interpenetrating dust into the heliosphere of this number 2 × 10⁻7 grams per cubic centimeter. If you put all this together, you can conclude that there's a column density of hydrogen atoms between 4 and 10 × 10⁻17, and a mass column density of dust between about 0.8 and 2.2 × 10⁻8 grams per square centimeter. This is to Alpha Centauri. So you're going to plow through all that stuff. Furthermore, the distribution of these grain sizes have been determined from both the astronomical and spacecraft measurements. And they're plotted here. The astronomical measurements tend to have a very sharp cutoff at a radius of about 0.3 microns. However, they're somewhat insensitive to larger dust particles. The spacecraft measurements indicate a flatter distribution with more large particles of order of micron in size. And if these are actually out there, those are fairly serious, these larger dust particles. So you have to take that into consideration. Okay, just a brief summary of the situation with the gas phase. These are mostly hydrogen and helium atoms. And this was a very nice analysis was done by Huang et al. Just came out in AppJ. Above an energy and material dependent threshold, atoms create damage tracks in materials. Below that threshold, the effect of the collision seemed to heal. The most damaging atoms are oxygen and iron. They concluded that highly conductive spacecraft materials are better off. And they estimated that 30% of a quartz surface could be damaged in transit to Alpha Centauri. A graphite surface, which is highly conductive, might fare better. Okay, then moving on to the grain collisions. They also recognize that the grain collisions are probably a more serious problem. Here's a cartoon of what happens when a grain collides with the spacecraft. And this is in the reference frame of the spacecraft. Now really, that's moving at 0.2 C, so I'm saying that the dust grain is hitting this at 0.2 C. At time t equals 0, it just enters the spacecraft material and passes into the spacecraft material in a time of about 10 femtoseconds, very short period. It'll stop in the material in about 1 picosecond. And then on a much, much longer time scale, the final damage will evolve, and you'll get a crater, you'll get some material that's expelled, and some radiation that might be re-radiated. So this gives a range of timescales that are involved in this problem. The energetics are kind of interesting. A single dust grain carries an energy of approximately 1/2 MV squared, and that's typically 26 joules for these parameters of density, radius, and velocity. That's an interesting parameter to me because most of my work has been done in laser matter interactions. And 26 joules is a kind of a nice, not an enormous laser, but a nice laboratory-sized laser. So you might actually think of trying to simulate this kind of process with a laser, a short pulse laser. The cumulative effect in going to Alpha Cent, you'll intercept 14 kilojoules per square centimeter. And if you just converted all of that energy into melting material, you could melt between 1 and 17 grams of material. And since we're talking about 1 gram mass crafts, that could be catastrophic. Now, it's not certain that that'll all go into melting. Some of it may be expelled from the spacecraft and may spread out. So similar estimates were done by Huang et al. They consider the overlap of damaged craters, and they concluded that these grains could damage a depth into the spacecraft of between 0.3 and 3 millimeters. Okay, I just want to say one word about, again, why I'm interested in this problem. This is a very interesting and challenging problem in the field that I work on called high energy density physics. And what that means is high density material that's heated to very high temperature. So here are some of the parameters: length scales, time scales, I already told you. Temperatures range between about 1,000 Kelvin, that's a typical melting temperature of material, up to 10 to the 8 Kelvin, that's 100 million degrees. In my world, that's called 10 kilovolt temperatures. So it's very, very hot. Energy densities range up to 10 to the 10 joules per cubic centimeter. So these physical parameters, they span many orders of magnitude. They're also, this maximum energy density and temperature are comparable to those at the center of the sun, which is very hot and dense, and also to that in inertial confinement fusion capsules, which we work on a lot at Livermore. So that's how I sort of sold this idea at Livermore, is to study this high energy density physics regime. That's quite interesting. Okay, so what I've been working on the last few months are numerical simulations of these collisions. We use a radiation hydrodynamics code called Hydra, which was developed for inertial confinement fusion at Livermore. this is basically a discretized description of matter and other processes. So we have finite difference solutions for the equations of hydrodynamics, heat conduction, and radiation transfer. The grain spacecraft interaction, which is a key thing, that's what drives all this, is calculated with an ion beam model that calculates the grain atoms as if there are ions moving through matter. And that's, we believe, an accurate model. We also have equation of state and opacity of the material. Those are treated with tables at low temperature. And then at high temperature, we use a time-dependent, we call non-local thermodynamic equilibrium rate equations. For any of you astrophysicists in the audience, know about that. And for these initial calculations, I've considered two types of grain atoms, oxygen and iron. Those are the dominant components by mass. And two types of spacecraft materials, a kind of a light element, silicon, and a heavy element, tungsten, just to illustrate or just to begin to understand some of the effects of choice of material. And so I've completed 1D simulations, and I'll tell you about those now. Well, first of all, let me tell you about the physics of the coupling between the grain and the spacecraft material. We use an energy loss formula given here. I don't want to go through the details. It's all defined if you want to read it or ask me about it. But it's important. There are two terms. One depends, it's a Z bound is the number of bound electrons on the atoms in the spacecraft. So this is due to collisions with bound electrons. There's also a term due to collision with free electrons that get ionized. And you have to account for both of these. And when you do this, then you see a temperature dependence in this energy loss. So it's important. Initial estimates were done just assuming the zero temperature formula. But if you account for these ionization and temperature dependence, you get a slightly different, you get a dependence of the energy loss on temperature. And note this is a log scale. So it's a fairly reasonable dependence on temperature. And there's also a very strong dependence on the material. Basically, the low mass elements, oxygen hitting silicon material, has a weaker energy loss. And as you go to higher either grain atoms or the spacecraft material, the energy loss gets much larger. So then we put this type of model into this hydrodynamics code, and I've done two types of one-dimensional simulations. First are longitudinal simulations. In this case, I consider constant properties in the radial direction and only ask how the grain couples to the background material and heats it up along the direction of motion. So here's the grain coming in. It's going to go through these zones in longitudinal direction Z and deposit energy. And so this plot gives the resultant temperature just after the grain has stopped in the different materials with different projectiles. And what you see here are very high temperatures. It ranges from 15 kilovolts for oxygen hitting silicon up to almost 60 kilovolt temperatures for the high mass atoms, iron hitting tungsten. And again, the heavier elements lead to faster stopping, higher temperatures. Okay, so then I went on and did one-dimensional simulations in the other direction, looking at the radial direction. So in this case, I see my lines didn't come out, but I have a finite depth in Z and just one zone in that direction, and then I have zones in the radius, and ask, now, once you've deposited this energy, and it gets deposited right at the smallest radius here, how that spreads out in radius. And well, first of all, to show this, I'm showing the temperature in the center versus time. And what you see is there's a heating phase. This is when the grain is interacting and heating the material up. And then a long cooling phase as this material is expanding and cooling by conduction and radiation. So this whole interval spans, this cooling phase spans about 8 orders of magnitude in time. So it's a fairly challenging numerical problem to simulate this, and it took me a while to figure it out. Okay, along with that, these plots show essentially the dynamics as a function of radius at different times. So the first on the left is a plot of the temperature versus radius. The earliest time here, the black curve is at 1 femtosecond when the material is still heating up. And the next curve, the red curve, is just at the end of the grain stopping. You reach your maximum temperature. And then these other curves are spaced at decadal units in time, logarithmically spaced. And you see the material cooling off and heating out. The center material cools off. The outer materials get heated up until you cooled off here at 1 microsecond. The density in a similar graph shows a shock wave propagating out from the center region that's been heated. That's a spike in density. And as that shock wave propagates out, it compresses the material outside, and the inside material expands. So ultimately, at the end of the simulation, you have a crater in here of a few hundred microns in radius that's been created by this. So that's one thing you can look at, is the evolution of that crater, which I showed. Another thing you can ask is try to estimate how much material will be melted by this, because melting is a damage process. We don't want to melt a lot of the spacecraft material. So the way you can do this is by looking at the energy density. So this is a plot. The color scale indicates energy density. It's a logarithmic scale. And it's plotted versus time along the horizontal axis and space in the vertical axis. So these are both logarithmic scales. And so what you see here is that the energy density starts out very high, early time at small radius. That energy then spreads out with time. And you can ask, when is that energy density equal to the energy it requires to melt materials? And that's this white curve. So all the material under the white curve has reached an energy density sufficient to melt it. The material outside has not. So you can actually calculate the mass of this material inside that's been melted, and that's plotted here for all the 4 cases of simulations versus time. And what you see is that the ultimate mass that's melted in these simulations is mainly dependent on the spacecraft material rather than the projectile material, the grain material. And it's about 6 times 10 to the minus 5 grams for a silicon spacecraft material, and about 2 times 10 to the minus 4 for tungsten. Both of these numbers are about a quarter of what you could theoretically melt if you turned all the energy of the grain into melting. So it's somewhat less. Now, a caveat, these are based on just 1D simulations. You really need to do 2D simulations to get a better handle on that. Another thing to look at is this crater that I mentioned, and the final crater shape. So the crater is defined as the material that's been evacuated by this heated region, and I define an aspect ratio for that crater as the depth of the crater, which is determined by the stopping of the grain atoms, and then the radius, which is determined by this hydrodynamic and thermal process. So this aspect ratio is Z over RC. That's listed here for these 1D simulations, the values of Z, the value of RC, and then this aspect ratio. So you have a very high aspect ratio for the oxygen hitting silicon, a low aspect ratio as you go up to higher mass elements. And I expect that the smaller aspect ratio is going to be favorable in that it promotes more energy loss from the spacecraft, and therefore less energy remaining in the spacecraft to do damage. But this is based on these 1D simulations. The caveat is, you really have to do the 2-dimensional simulations to study this energy loss, including mass loss, radiation loss, and also another effect I haven't included in 1D is stress-induced material damage. So this is a kind of a qualitative picture of what I think would happen. Okay, so I've done a very preliminary 2-dimensional simulation, and I just want to show these cartoons of this. Well, they're actually plots of this result. These are plots of the density in the matter on this scale. The maximum density is about 3 grams per cubic centimeter. And I show each panel is a different time in the simulations. So what you see early time is a very thin, low-density regime at R equals 0 in the center of this heated cylinder, and a shock wave that then expands outward, this dark strip, and it continues to expand outward with time. Ultimately, it dissipates, becomes very weak. And then you see this crater growing with time here until it kind of reaches a final size here. And you see a little lip on the crater here of material that's been pushed out but not completely evaporated from the spacecraft. So it's these type of simulations that I would propose to work on further to really quantify how much material is removed. Okay. I want to mention some ideas that my colleague Tim Early and I have been thinking about that in order to reduce damage to spacecrafts. So some fairly simple ideas. One is to optimize the spacecraft geometry. That is to minimize the front surface area. I don't think you should fly kind of face forward. You really need to fly edge forward through the interstellar medium. And it would also help to make the craft, rather than square, make it long and skinny so that the surface area at the front is minimized compared with the area that you can use for taking pictures along the sides. Incorporating a protective shield I think of order 2 millimeters is probably is an important thing to do. This could have several different layers. Choosing the right materials, there's a trade-off, it looks like, between high conductivity, high melt energy, and energy loss. And the optimal is not yet clear. It requires further work to try to choose the right material. Another idea I'll describe in a bit more detail is incorporating a thin foil ahead of the spacecraft. So here's this idea in cartoon form. Here the spacecraft is moving to the left, the dust grain, in the reference frame, the dust grain is coming from left to the right. If you put a very thin foil out in front, the dust grains will penetrate through this foil and get heated up. They'll get atomized and ionized. And these atoms will fly off in some cone of directions. Some of them could miss the spacecraft, so that kind of helps you avoid damage. As well as the atoms that do hit the spacecraft, we believe in net will have less damage than if the grain hit the spacecraft itself. So an example is you might have a 20 nanometer gold foil, approximately a meter in front of the spacecraft. That would heat up this grain to 6 kilovolts temperature, sufficient to explode it. The spread of the grain atoms is about 1 centimeter in that 1 meter, so some of those would miss the spacecraft. If you could put this 10 meters in front, it would be even better. Okay, so some future work, briefly summarized. There's some improvements to be done in the two-dimensional simulations. I won't go through the details. I would propose doing calculations with real grain compositions. So far, I've only done them with single atom compositions, which is somewhat idealized. And then it would be important to do a broad survey and optimization, studying a bunch of parameters and trying to find the optimal. Such as, well, in terms of finding optimal, you would vary the spacecraft material and the possibly multi-component materials. And then I want to do simulations at a variety of velocities and sizes. So let me just put up my summary and mention the bottom line here. These analysis tools, numerical simulations I presented, can be used now for engineering design to optimize spacecraft materials. And that would be nice to do in future work. Thanks.
We have time for 1 or 2 questions, and if you have a question, please go over to the mic. That way everybody can hear.
Do you have any concerns about cosmic rays or high energy cosmic rays?
You repeat the question since the mic was on.
Do I have any concerns about high energy cosmic rays? Well, let me say I haven't thought too much about that. I think the problem for that is really not much different than it is for low velocity spacecraft, such as interplanetary spacecraft. So I think there's others in the audience perhaps that know about that situation. These problems that I talked about are particular for these high velocity spacecraft.